These are applications of implicit differentiation where two or more variables are changing. I'm going to say, remember to take the derivative of every variable. I'll get out of the way here. Can't see. Okay. These questions are cool. I know we have 3 days left. Okay, but these are the types of questions that calculus was made for. Okay? Because these are rate of change questions, but where the rate of change changes. Ooh, to get deep. The first example is going to be blowing up a balloon. Okay? If you think of the radius of a balloon, if you blow up a balloon this big and I blow it this distance, or the balloon is this big and I blow it this strength, which one's going to be growing faster? Sorry, the second one's going to be growing faster? The first one for sure because it's only small, right? But the point idea is the rate of change of the radius, right? The radius will not be growing at the same distance here versus if it's like the size of this room and you're putting in a little bit, right? Or the same thing with, like, let's say a pool, okay? And you're looking at the height of, you're filling up a pool with the height of the water and it's like an in-ground pool. When the pool is empty, okay, and you're down at the deep end and the deep end's only this big, it starts to grow really fast. But when the pool is almost full, it feels like you're never going to fill it up, right, for those of a pool, okay, right? So this is the same thing, depending on, again, there'll be multi-variables that we're going to be dealing with in here. Does that make sense, sort of, or that's what we're heading into today, okay? So today's example, which is example 1, says, air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. Determine the rate at which the radius is increasing when the diameter is 20 centimeters. Okay, I'm going to get out of the way, give you a chance to write it down so you're not scribbling and trying to listen at the same time. It's one of those difficult. One thing I should just say while you're writing, please start to bring in cans. Okay, I've forgotten as well too, so I will bring some in this week. Please try and bring in as many as you can. All competitiveness aside, it's for a good cause, right? So.
What's the prize again? Like a pizza break?
What's the prize? The glory of doing well.
Well, I know, but it's.
I'm not sure if there is. Teresa, is there a prize for?
Yeah, the prize if you're part of doing good.
Pizza party.
That's what I thought it would be too. That's enough.
Yeah,
Oh, I definitely will bring them. I'll probably bring them in anyway.
So you made a good joke there,
that was glorious. As many as you can.
Oh. Okay, so let's go through here. Let's talk about some of the variables that we're going to get into. There's a lot of stuff going on in this question. When it says air is being pumped into a spherical balloon at a rate of 5 centimeters per minute, what's changing? What's changing there? If air is being pumped in. Go ahead.
The volume of the sphere.
The volume of the sphere, okay? So I'm going to call that this is going to be the rate of change or volume. Now before I move on here, I have to call it dV by dt. You could have called it dV by dx. You could have called it whatever you want. But the idea is that the volume is changing. Is everyone in agreement with that before I continue? Like the volume is going up each time. Okay, someone other than Derek. What else do we know in this question? There's at least one more thing we know. Let's go ahead.
So, like, we have to solve, when the diameter is 22.
Good, so what's the radius gonna be when the diameter is 20?
10.
Yeah, so my radius is gonna be 10, we're given that. What's our unknown? Somebody help me here, what's my unknown gonna be? So the question is where does 10 come from? We know the diameter, I'm just being a mean math teacher, diameter is 20, so radius is 10. I'm just being a, the mean math teacher. Sorry, you're out, I'm sorry. Two guys are out, somebody else here, what are we looking for in this case? Rate of change of what? Rate of change of the radius, right? So dr by dt equals unknown, and that's the rate of the change of the radius. Okay. Okay, now let me just slow down here and make sure that we're good, because the math isn't hard for this. The given information is the hard part. James, you guys say okay, you got a haircut?
Yeah.
Very good. You feeling sort of okay about those three things? You just gotta read through them right. So it's gonna the rate of change of volume and the rate of change of radius, and then we're given the radius. Yeah, Bailey, go ahead.
Why did you give us the rate of change of volume?
Because we need it. I'm gonna show you right now why. Are you ready? Because the thing is, this is what I was saying. Okay, guys, listen, please. This is what I was saying again about if you're, like, let's say you're pumping up a big giant balloon for your wedding, okay, and your balloon's going to be this big, and it's going to say, "My wedding is today," or "Happy birthday, Mr. Sadler," is what it's going to say on this balloon. But the balloon's the size of the school. Okay, the idea is you're going to be using a pump, and it's going to be pumping at a constant rate. The idea is the radius is going to be changing more. You know what I mean? The rate of change is more when it's small versus when it's the size of this room, right? That's what we're saying. So you're going to need that.
So then, if that's the case, and we're trying to find the rate of change radius,
Yeah.
We have the ending radius, but don't we need like an initial radius?
No, we don't.
No.
That's the magic of calculus. Here we go. Okay. What's the equation for the volume of a sphere, please? No. Close, but no.
2 pi r.
Okay, so let's implicitly take the derivative of this. Luke, you're up. What's the derivative of v going to be? What's the derivative of v going to be? Forget about that. Start with the v. V is just going to be dv by dt. That equals whatever. Okay? So this is just going to be, that's how much the velocity, that's how much the volume is changing. Everyone see that? dv by dt or dv by dx or whatever. It's just going to be the change of velocity. Michael, go ahead. Yeah, this is one that I would give you for the test. This is like a grade 9 formula sheet. Remember I gave you that formula sheet before? So that one I would give you if you need it. Okay, so keep going, Luke. What's the derivative of 4/3 pi r squared? Or pi r cubed?
4 pi r squared.
And I'm just going to put in here the implicit part, dr by dt. That's what I think. Yeah?
Isn't that the, yes,
I hope not. Did I mess it up?
That's right.
Somebody just want to check? I think I have it right.
yeah.
Am I good? Somebody just check for me because now I'm worried that,
Did you put the dr?
yeah, but 4/3, right?
But,
Yeah, you
yeah,
had it
no,
right.
the same, no, the answer is the
It is, yeah, that's right, I got the mistake. Yeah, and that's the nice thing you'll notice about, sorry, I didn't understand what you're saying. Yeah, and that's the nice thing, I tried to show some people this, the derivative, always, when you go to volume and surface area, they always, that's how they get the equations from. Actually, it's magical. Math is magical, this is another example of being magical. Chris, go ahead.
So, you put the dr over dt because of the r there, right?
Yes.
Okay.
And the same thing, put the dv by dt because of the v there. Okay, so now we just sub in the numbers and we solve, okay? So dv by dt is equal to?
5.
Equals 4 pi, r is equal to?
10.
And then dr by dt.
That easy.
That's all it is.
Go ahead.
That's just the rate of change of the radius. So that's just like the derivatives we were doing before. When you take the derivative, remember y, you just call it dy over dx. So this is just gonna be the change, the dr over dt is the rate of change of the radius. So when you take the derivative of r, it turns into dr by dt, that's what we're saying. Yeah. Yeah. Right, because if you do r cubed, I'm calling that 3r squared dr by dt.
This is not
You know
understandable.
when and when not to do something or something.
It's basically, it's gonna be, I mean, you could do it always, that's what I'm saying, but if it's for a regular question, you can do it like that too. But you don't have, for these ones, if I, whoops, on this test, always, it's gonna be, okay?
So what you're asking for is what you're probably gonna want to get
Yes.
on for the,
Right, and that's what we're looking for here, we're looking for dr by dt, so we know we need to. The rate of, whenever you're looking for the rate of change of something, right, that's when you're gonna go with it. So this is gonna be a little bit messy, I'm gonna call that 5 over 40 pi.
Should the tens be squared?
Yeah.
Oh my goodness. Mr. Sadler, you're slipping here. 5 over 400 pi, how's that?
Better.
Beautiful.
So that's 1 over 80.
400 pies. That is.
Therefore, the
Yeah,
radius.
like 10. There you go.
when you need to form the size.
Oh, right. I forgot that we should have put in decimals.
Okay. We'll leave it with 1 over 80 pi. Now, the nice thing is about this question, okay, guys, is once you get the derivative here, let's say I want to find the rate of change at 2 centimeters. You just plug in a 2 here, right? Or at 11.9 centimeters, just plug in 11.9, right? Like it's just the setup of these ones that's trickier. Okay, like the math isn't super difficult. It's just the setup that's going to be the hard part. Okay? Have confidence in yourselves. You can do these. Okay? And people always get worked up because of the word problems. That's always what happens to people. Chris, go ahead.
You did seconds, but how do you know?
Because time is seconds. Radius is radius per time. Centimeters per second.
Oh, okay.
And that's for volume, right? Centimeters cubed per minute. I probably should be per minute, shouldn't it be?
That's what I was thinking. It's like
Sorry,
that's
that should be per
like
minute.
per minute, and that's per
Sorry,
second.
that's before. My bad. All right, example 2. Oh goodness. Okay. I gotta tell a joke right now. Is it time for a joke? It's time for a joke.
Are you telling us a joke because it sounds like really hard, and you want to make us feel
Okay, it's time for a joke.